So, tutorial sheet 2, question 4. First part of this question, it's quite a long worded question, but we need to extract from it the useful information that we need. So the first sentence which says, an AM double sideband transmitter developed an unmodulated power output of 1 kilowatt across a 50 ohm resistive load. So first of all, let's recall the equation for the power in an AM double sideband system, which is given here. Now the question states that the unmodulated power is 1 kilowatt. So unmodulated means that there's no modulation. In other words, that M is equal to 0. So in this case, PT is equal to PC, which is equal to 1 kilowatt. And that power is going into a 50 ohm load, 50 ohm resistance. So that's the first bit of information that we're given. The second bit of information says that when a sinusoidal test tone, in other words we're adding some sinusoidal modulation into the system, when that is applied to the input of the modulator, it is found that the spectral line for each sideband in the magnitude spectrum of the output is 40% of the carrier line. Well, what does that mean? Well, if we look at the frequency spectrum of an AM signal, well, we know that we're going to get a carrier component at the carrier frequency, and we're going to get two sidebands, one at FC plus FM and one at FC minus FM. And the amplitudes of these, well, the amplitude of the carrier is very simply VC, and the amplitude of the sidebands is MVC over 2. And what the question is actually telling us is that the amplitudes of these sidebands is 40% of the size of the main carrier component. So in other words, that is equal to 0.4 times VC, which of course is equal to MVC over 2. And if we rearrange that, we get M is equal to 0.8. So that is our answer for part A, which is asking for the modulation index. Now the next question, part B, asks us to work out the peak amplitude of the lower sideband. Well, it's a bit of a red herring, to be honest, because the lower sideband and the upper sideband both have the same amplitude anyway, so it doesn't matter which way around you think about it. So, but we need to work out what the peak amplitude, the peak voltage of this lower sideband signal is. So how do we do that? Well, first of all, what do we know? We know what the carrier power is from our initial numbers that we were given. So PC, which is equal to 1000 watts, is also equal to VC squared over 2R, because this power is going into a 50 ohm load. If we rearrange that, we get VC is equal to 316 volts approximately, because R is 50 ohms, so we can simply rearrange that equation. Then we want to, from this, we want to work out what the amplitude is of the lower sideband. Well, we know that the lower sideband, or either of the sidebands, has an amplitude of MVC over 2. So in other words, VLSB is equal to MVC over 2. And we know VC, and of course we know M, which is 0.8, so that's 0.8 times 360 over 2, and that gives you 126.5 volts. Okay, moving on to part C. Part C is asking for the ratio of the total sideband to carrier power. Well, hopefully by question 4 we've done enough of these by now. So if we say, well, what is the sideband power divided by the carrier power? Well, the sideband power is PC m squared over 2 from this part of the equation. The carrier power, well, that's just PC. So we very simply that cancels, and we get m squared over 2. If you work that out, you get 0.32, which is the answer to part C. Part D is then asking for what is the total output power given everything that we've got so far. So the total output power using the equation above is 1000 for our carrier power into 1 plus m squared over 2. And if you use the value of m that we have, which is 0.8, we get an answer of 1.32 kilowatts. Okay, so moving on to E. E requires a little bit more thought. This one's a bit often catches students out a little bit. So we need to determine the total average power output if the peak amplitude of the modulation sinusoid is reduced from 5 volts to 4 volts. So in other words, our input signal is reducing in voltage. For all this question, we were working in very high voltages. So for instance, VC is 316 volts, etc. So the first mistake that students often make is to use that those values of voltage to then work out what Vm is. Well, in reality, a system works at much lower much lower powers. So we have, for instance, our modulator here, and we have some oscillator which has got a VC and it operates at FC. And we have some signal going in here, which is our Vm, which is also operating at FM. And we have so this is our AM double sideband carry present modulator. And we do this at very low voltages, because when we do that, it's actually a lot cheaper to do things at low voltages. And then we go into a high power amp. And at that point then we can transmit it into free space. So for all of the questions so far, we've essentially been working out the powers and voltages at this stage, so the high power stage. Now the question in this case is actually saying, well, if my initial modulation is actually, which is at a much lower voltage. So initially it says Vm was equal to 5 volts, and now that is going to change and go to 4 volts. So because this is a linear system, all we're saying is that if 5 volts, that gives us a modulation index of 0.8. So in other words, what does 4 volts give us? And because it's a linear operator, it's just the ratio. So now our new modulation index is going to be 0.8 from here, multiplied by 4 divided by 5, because that is the ratio of what we're changing to. So we're reducing by a factor of 4 over 5. We need to multiply that by our new modulation index, and that gives us a value of 0.64. So that's our new modulation index by reducing the voltage from 5 volts to 4 volts. So now the new output power, total output power, nothing else has changed. Remembering we're at this after the high power stage, it's still at 1000 for the carrier power, plus our new M, which is 0.64 squared over 2, which is equal to 1.2 kilowatts.